In introductory spectroscopy courses, instructors and textbooks are generally very careful to show proton-proton spin-spin coupling patterns that are first order. This requires difference in frequencies for two peaks is at least 8 times greater than the coupling constant for an individual peak. In the Pople notation, when the peaks are well separated, we generally will use letters at each end of the alphabet, whereas when the frequencies are much closer together, but not chemically identical, we'll use letters that are next to each other in the alphabet. The example on the left is an example of AX coupling with a large difference in frequencies for relatively small coupling constant J. But as this ratio decreases, we see distortion in the arrangement of the multiplets. In fact, this is even an apparent quartet, but in fact it's not a quartet at all. These other patterns fall in a large category known as AB coupling. The following definitions are required for a simple first-order multiplet that is easily analyzed, including a ratio for the difference in frequency over the coupling constant, number of peaks in the multiplet equal to n plus 1, and a centrosymmetric multiplet. This example with bis chloroethyl ether is instructive in what happens when the frequencies of multiplets are close together. At 60 megahertz, which is an instrument I fondly remember from my undergraduate research days, all we can say is that this is a featureless multiplet. At 300 megahertz, the situation improves a bit, but it's still not the ideal two triplets due to some second-order effects. This is a big advantage of the high-field NMRs in that we now get sufficient separation between the chemical shifts of the two triplets, or the frequencies of the two triplets, so that we see a clean resolution and first-order triplets. The textbook describes one nitropropane. This is an AMX pattern, specifically A2M2X3, and we see that there is sufficient separation of frequencies even at 90 megahertz, so that we see two triplets flanking the internal methylene. On the right is a list of frequencies from which we can actually determine the actual coupling constants, J. By subtracting differences between the Hertz values, we can determine that the A2 triplet has coupling constant of about 6.8 Hertz. Going to the right side, the methyl triplet has a coupling constant of 7.5 Hertz. The apparent sextet, in fact, is going to be a mixture of the 6.8 and the 7.5 Hertz couplings. So this is, in fact, not a true first-order spectrum for the M2 resonance, although we can say that it is an apparent sextet. For styrene at 90 megahertz, the C6H5 section of benzene is hopelessly convoluted due to very small differences in the frequencies for the aromatic hydrogens. But for the alkene hydrogens, the three alkenes can be clearly distinguished. Moreover, we see that at 6.8 parts per million, we have a doublet of doublets, whereas the peaks between 5 and 6 are two doublets with different coupling constants. For two chemically non-equivalent protons, even though the frequencies are fairly close together relative to the coupling constants, the list of frequencies on the right reveals that the situation is a little bit more complex than at first inspection. For the doublet of doublet around 6.7 parts per million, we see a difference between the first two peaks of about 10.8 hertz. We round this off to the nearest tenth of a hertz. The numbers are not really more accurate than that. And the other doublet, also about 10.8 hertz. And then these two doublets are separated by 17.6 hertz. And that's the doublet of doublets. For the next apparent doublet, around 5.7 parts per million, we see it's more complex. There's actually a small doublet of about 1.1 hertz that is then separated from another 1.1 hertz doublet by 17.6 hertz. So the resonance around 5.7 parts per million is also a doublet of doublets. The remaining apparent doublet also has 4 lines associated with it. The first two separated by 1.1 hertz, and then the difference between these two is about 10.8 hertz. So this is also a doublet of doublets. We can assign each of the hydrogens of the alkene of styrene. One bit of information that you will read in section 3.13 on the magnitude of coupling constants is that hydrogens with a dihedral angle of 180 degrees have a slightly larger coupling constant than hydrogens separated by a dihedral angle of 0 degrees. So hydrogens that are trans to each other on alkenes have larger coupling constants than hydrogens that are cis to each other on alkenes. This tells us that the 17.6 coupling constant must belong to the hydrogens that are trans to each other, whereas the 10.8 coupling constant is for the hydrogens that are cis to each other. And the two hydrogens on the same carbon are chemically non-equivalent. One is trans to the benzene ring, the other is cis to the benzene ring, and these have a coupling constant of 1.1 hertz, which is fairly typical for an alkene with dihedral angle of about 120 degrees. We'll now assign the specific alkene hydrogens. The first one is at 6.71 ppm. This is 1H doublet of doublet, coupling constants of 17.6 and 10.8. The next hydrogen is the one that's trans to the 6.7 peak. This is at 5.70 parts per million. One hydrogen, doublet of doublet, with coupling constants of 17.6 and 1.1. And then the remaining alkene peak is at 5.22 parts per million. One hydrogen, doublet of doublet, with coupling constants of 10.8 and 1.1 hertz. I hope that was pretty straightforward. But now let's go to a case that is not uncommon in my lab and probably in many of your laboratories. This multiplet is depicted in figure 3.26 on page 143. This is probably a simulated multiplet because of the nice sharp peaks, but this is a good place to start. I'll talk in a moment about how we come up with all of these couplings that are shown below here. But let's first discuss some rules, which are based on an article from Tom Hoy's laboratory from about 25 years ago. Paul Hansen, now a professor at University of Kansas, and Jim Vivian, now a professor at Western Washington University, were graduate students who contributed to this publication back in the 1990s. And the rules I will mention are paraphrased from page 143 of the textbook. The first task is to integrate each line of the multiplet, and I'll show you how you can check your work by the sum of these integrals being a power of 2. Then we find the first pair of lines, and this will correspond to the smallest coupling constant. We want to identify if the intensity is a doublet, a triplet, or a quartet. Then we go throughout the spectrum, finding all of the pairs or triplets or quartets that are separated by the smallest J value. We'll then identify the centers of each pair or each multiplet that's created, and we'll find a new simplified pattern. And this will be the next smallest coupling constant. And then we repeat this process to find the remaining coupling constants as they increase in magnitude. So let's go back to figure 3.26. The first rule is to integrate each line of the multiplet. I will write the numbers above the peaks. So this is 1 to 1. So it's pretty clear that we'll be looking at a doublet for the smallest coupling constant. Now, for the next peak, the third peak, you might ask, is this 2 or is it 3? Because it might be difficult to tell by inspection. This is where the ability to check our work with the sum of the integral values will be important. But if we assign these to be 3, and the small ones are 1, 3, 1, 3, and now we're at the midpoint. In an ideal multiplet, this now reflects. And the key now is to check our work. And if we sum all of these together, we come up with the number 32, which is equal to 2 to the 5th power. Notice if we had used 2's for all of these values, we would come up with 24, which is not a power of 2. And so that allows us to say with more confidence that these bigger peaks are 3 and not some other number. This first pair is separated by about 4 hertz. Then we find the other 4 hertz differences. And I've done this quickly. And now we assign relative values to each of these pairs. Once we reach a midpoint, I think it's a little bit easier to complete the series. We now find the next pattern. In this case, we see 1 to 3 as our first connection. And so we should look for another 3 and 1 to connect things. That looks like a quartet. And then we can find another quartet, 1 to 3 to 3 to 1. The difference in these peaks measures at 7 hertz. So we've established a doublet coupling constant 4 hertz and a quartet coupling constant of 7 hertz. What then remains is to link the quartets. To find that difference, I recommend working back along the path of each of the 2 quartet components. For the other quartet, also work in the same direction, in this case, toward the left. And that reveals that the last coupling is a doublet separated by 12 hertz. Now that I've shown you how this is done, I will share with you that I really believe that the only way that you can really learn this is to do it yourself. And so I actually recommend printing out, or if you wish to project on a screen, on a blank tablet, this spectrum, and then practice this yourself until you're comfortable with it. Let's go to some spectra that are not simulated. This is an example from Hoy's paper. We see 7 lines, but it's not a classical septet because it doesn't fit Pascal's triangle. But we can apply the same principle. In this case, I've converted the parts per million values into hertz. When you actually take your own spectra, I recommend along the bottom horizontal axis, print out parts per million, but along a top horizontal axis, print out the frequencies in hertz so that you can check the coupling patterns. The MNOVA program, in principle, can do this for you. On occasion, it does this correctly. On many other occasions, it does not. And so it's important for you to be able to inspect the MNOVA information and to deduce it yourself if MNOVA doesn't do the job. Well, I've been philosophizing about the strengths and weaknesses of MNOVA. I've come up with a coupling pattern. At 5.87, one hydrogen is a doublet of doublets with coupling constants 4.5 hertz, 10 hertz, and 16.5 hertz. Again, try to do this on your own. The last spectrum. In this set of data, Hoy has presented the multiplets for hydrogens at 3 contiguous carbons. I don't have access to the complete spectra. These are just the 3 that he highlighted, probably because they did not overlap with other peaks. Hopefully, it's pretty easy for you to look at the first one at 1.85 and the last one at 0.15 and determine that each of these is doublet of doublet. For the 1.85 multiplet, These are coupling constants of 3.5, 10.5, and 13.5 hertz. For the 0.15 multiplet, this is a doublet of doublet of doublet with coupling constants 1.5, 5.0, and 8.5 hertz. This one in the middle is more difficult, and so let's look at an expansion, which you can do with the MNOVA program by simply zooming on a specific multiplet. The hardest part, in my opinion, to get started is to assign the relative integrals. But the first two, I think, are probably 1 to 2. The third and fourth one are lower, and there's some overlap. So perhaps it's not unreasonable to think that those are fundamentally ones. And then the big one, if we make that a 3, so far our sum is 8. And if we look at the reflection on the other side, the sum is 16, which is 2 to the 4th power. We've actually completed the hardest part of this exercise. Now it's a matter of simply finding the patterns. The first two peaks are separated by 3 hertz. So I look for all of the 3 hertz patterns, 1 to 2 to 1 for a triplet. Here's another one that is, keep in mind it's 1 to 2 to 1, even though that second one looks, and third one is a 3. So this is where it's worth going to the other side, building from the right side. Again, I see 3.5 hertz, but again, there is a little bit of error in these numbers. And now I see where those 3 peaks are making sense with a 1 to 2 to 1 triplet. Okay, so we have 4 triplets. And the triplet coupling constants are averaging about 3.5 hertz. Each of them is 1 to 1 to 1 to 1. Now we see a 5.2 hertz connection. And then we have a larger one that's at about 8.2 hertz. And that completes our analysis.